Yep. So we're considering the following system. Its state vector is in the vector space Rn. Its control is from Rm, and it is guided by the following system of ordinary differential equations with the A matrix being of dimensions n by n and B matrix being of dimensions n by m. So we want to try to understand the approximation of the state in which the system will get after the interval dt. Each dt we generate new control. So now we are taking a closer look into a single step of that. And formally we can write it on this. We're interested in the explicit form of the function, function of time, like this. So this is the beginning of the interval, and this is varying time that is in between of 0 and delta t. Let's take a closer look at this equation over here. We can find its equilibrium point. What is the equilibrium point? Where the system is not going anywhere, so the time derivative is 0. If we are not in the equilibrium state in any other state, the behavior of the system will be non-trivial. It will be changing its state. But if the time derivative is 0, we're just staying in the same state, and that's it. So equilibrium point, the system is dot equals to 0, and at the same time it is equal to ax plus c. So we can rearrange this and get ax is equal to minus c, or if the matrix A is invertible, which we will assume it is, the x star is equal to minus A inverse c. So I state that if our system is in this state, it will not go anywhere. It's the equilibrium point. What we can do next is we can change the variables. Let's introduce variable.
The equilibrium point is 0, 0, right? So
The equilibrium point, no, the equilibrium point is this one.
it can be anything.
It is, so for this form of differential equations, the equilibrium point is set by this expression over here. We're now not considering any specific system, we're just considering the very general case. Very general case is this form of linear systems and sample and hold control. So we are momentarily commanding certain control, and it could be acceleration, for example.
So
if
right
we
now we're not considering the example of the mass here. We're not considering the example of the mass, we're just considering a genuine discrete system.
yes,
Described
so
by-
it's the system with the mass is described in the same framework, really, but we're not considering any specific system. And it's important to understand that the system that we are going to analyze here, that we want to obtain, it's the discrete approximation of the real behavior of the continuous system. The control is discrete, but the evolution is continuous. The evolution is given. The world is continuous at, well, up to Planck length or Planck time, but it is, kind of. So let's change the variables. Let's introduce y that is equal to x minus x star, and it will mean that x is equal to y plus x star, so minus A inverse c. Let's just plug this into the equation, into this one, and see what happens. And x dot is equal to just y dot, because this is a constant, and if we differentiate it vanishes. So y dot is equal to a times x, and x is this expression over here, y minus a inverse c plus c. You see where it's going, right? So it's ay minus a inverse c plus c. The a and a inverse cancel out, so we get just minus c plus c. They cancel out, and what we get is just y dot being equal to a y. So we have simplified that equation. And
y is the error. What is y exactly again?
Y exactly? It's not the error. So imagine that momentarily at this period in time we are commanding acceleration. Commanding this acceleration will not make sense outside of these time limits.
Yeah.
So it's not exactly the error, it's the difference between the current position and the origin. This origin, or this equilibrium point is better to say, yes. This equilibrium point is not any kind of special or anything like this. It's just a tool for us to rewrite this equation in a convenient way. So nothing special.
Sorry, can you like go back a bit? Like, so we have x. Okay, so x is representing the state of the system at a given point, right? And from x, we have to. So we are applying control for a small time delta t.
Yes.
Okay. And let's take the so x of k delta t plus t. What do we mean there? So
here.
Can we the x of k delta t plus t?
This. It's the thing that we want to find is the function of time that will give us the trajectory of the system in this time interval, in this one. So this is the starting point, the moment of time number k. The beginning of the interval when we started exerting this control.
Okay.
And this thing changes from 0 to delta t from now to the end of the current time interval.
Okay. So t is the starting time point.
K delta t is the starting time.
Right.
Yes. And t is changing from 0 to delta t to end of the interval.
Got it. Okay. That makes sense. Now we're trying to describe x as a function of t.
Of time, yes.
Okay,
Time,
within that
from the
time.
beginning of the interval.
Okay, within that interval, we
Yes.
want to describe. Okay.
Exactly.
Now, let's go into the equilibrium point.
It's just a mathematical trick, no real deep sense over here.
Okay.
We're simplifying this equation.
Got it. And so, let's see.
What says y again? What says y?
Why we have substituted, it's just a variable substitution, so we are rearranging the equation for it to take the convenient form. We have just subtracted the equilibrium point from the state. Linear change of coordinates. So
How do we set x dot to 0? In that interval, how do we know it's going to be 0?
It's the equation from which we can actually find out this 0 point, or not the equilibrium point. So if a certain point is an equilibrium point, then
Can we define the equilibrium point? Can we in that time interval, what do we define as the equilibrium point?
the equilibrium point is point in which the system is not going anywhere. It's not. Well, basically, the criteria is that x dot is equal to 0. So if we are in that point, we're not going to go anywhere.
Okay.
If the marker is flying, then it's at any point in non-equilibrium point.
Okay. So here x dot, so x dot is not just within, we are not considering x, we are considering x dot as in general, the equilibrium point for the, not within this interval.
Yes, not
It's
within
not
this.
within, okay.
Well, it's the equilibrium point is in the state space, and the interval is in time. Not
The
really
interval is
depends.
just a short duration within the.
It's in the time domain, and the equilibrium is a certain point in the state space.
Okay. Let's say we have this graph earlier, right? Sorry. So we had this graph earlier, like applying discrete units, like so. At this point, let's say, for example, we're considering this interval. Do we at any point in this interval have to get to the equilibrium point? No, right?
No,
we don't.
So,
Yeah, that makes sense. Yeah.
yes, it's a convenient trick.
Got it.
We don't want to approach it. It is not of any special interest. We want
Right.
to obtain the certain form of the system evolution. Can we go further, or another question?
So is that the equation, this equation is the same as the equation that you gave us before? Which equal to b?
Yes. So this is the general form of the equation, and if we plug for a certain time interval the same control, constant control, we can just change it to this, because the constant matrix times the constant vector will be another constant vector.
So here, in this case, the control is fixed.
Hmm?
The control is fixed at the.
Yes, for a fixed time interval, for a short time interval. We first sampling control once
So
every
we
10
are
milliseconds.
sorry, so we are fixing the control and we're just studying the case on a changing time.
Yes, exactly. Inside of the fixed interval. So if we're sampling control every 10 milliseconds, we fix the control, then the system evolves, then we generate new control, and the system again evolves. And now comes the awesome part, because we know how to solve it.
E to the power of a matrix.
Yes. So. Okay. Let me define that. So, e to the power of a matrix is a series that is defined in the following way. Oh, yeah, let me call this K. So yes, it's a series like this. And it's a generalization of the same thing going on in one dimension.
Okay. Isn't that just like the Taylor series?
No, it's not. It's not a data series or a time series. It's a power series.
So we are okay. So we're just representing it as a like so e to the m. Like we would represent e to the x for like any like the function e to the x. We can write it as that, or like instead of m, we would write x to the k. Sorry, yeah. We would write the Taylor expansion of e to the x in the same way, right?
Yes.
So we just instead of
Yes. The Taylor expansion will be just a couple of the first terms, disregarding the rest.
And we're using okay. So instead of x just being a number, we're just putting a matrix in there.
Yeah. Well, for the values for the numbers, it's defined as this series, and we're slightly generalizing to the matrices.
Okay. Okay.
It's okay. Everyone is happy.
Okay.
Great. So. Yeah, we're almost there. So here should be y from the moment k delta t, right? Let's keep the same notation. It's a bit tedious, but let's do that. So y is living in the same time. Y of k delta t, which is a constant, plus t is equal to e to the power of at times y from k delta t. And now we can get back to the x, which will give us the following. Well, what is y at k delta t equal to? Y at k delta t is equal to x at k delta t minus a inverse c, so like this. And now we can indeed consider a first order approximation for e to the power of at. So e to the power of at is equal to an identity matrix plus a t plus higher order terms. Let's plug it here. Well, we will use approximation. It's kind of inaccurate, but let's do so. Identity plus at times x at k delta t plus a inverse c. Okay, let's just keep the first part intact. So it's e plus at x k delta t plus a inverse c plus t a inverse c. We're almost there. So these two cancel. And now we can plug back this c, right? Let's do it. please double check if I'm not mistaken.
Yeah, the question. So the first part here, when you expand I plus AT times, but then when you multiply I with like any matrix, shouldn't I be like done?
Shouldn't.
Because I, the identity matrix multiplied by any matrix should be equal to the like the other matrix, right? Or no?
Could you? Yeah.
I mean, this part here, multiply I by AT.
No, I'm not multiplying. It's the addition. Or
No, I mean this one addition, right? But you expand?
yes.
Okay. But this one multiplied by this one, you should get this one here. Right, and the I should be.
I just expanded the second part.
But this one is it.
Yeah. So this, just check that. I could miss something. Hope I did not.
This x k delta t plus t, isn't that equal to y plus the equilibrium point?
Yes. You know what? I forgot to subtract, right? I forgot to subtract.
Wouldn't you have to add
x star.
y plus x k x?
Hmm?
Wouldn't it be y plus x? Like y plus the equilibrium point is equal to x. So like, is that right?
Could you repeat?
So we went from y k delta t plus t. We went from that to x k delta t
Yes.
plus t is equal to. How do we do that? Like y is equal to x minus.
Yes, I forgot to subtract minus x star.
Shouldn't it be plus x star?
Yes, it should be plus.
Plus
Yeah,
x star.
so plus x star minus this thing, right? Over here.
Oh, right.
Yep. So sorry for that. Minus a inverse c.
Yeah.
Yes. Sorry. And it's approximately equal to this thing. Okay, I'll just add that. Minus a inverse c minus a inverse c. Nice. It cancels out over here.
Right.
Again, please where was a inverse?
Yeah, so
X inverse.
I was mistaken in the backward substitution. X is just equal to y minus this constant, and I forgot to write it here. Okay, so what we are left with is the following. These two just cancel, this stays the same, and also we have here plus t times the constant c, which is nice because we can now plug back c from there, and we get the following. Identity plus t times a times x k delta t plus t matrix B and the constant control. And do you follow? All of you follow, right? And the last thing that we need to do is we have to consider this system at exact moment in time where t is equal to delta t. So x of k plus 1 delta t is exactly that. And we'll substitute here t by delta t, which will give us.
Okay.
Watch closely. So it will be e plus delta t a x at the first instant in time plus delta t b uk, and this is our matrix B hat, and this is our matrix A hat. Да.
Excuse me, should I send for someone the
I think it should not take long.
So,
No, no, I just didn't really did it.
will be available on electronic version?
I can't do it. I can do that, but my signature won't be hard.
It's me.
No, you and like the one from the department.
Okay, but they can sign first and
Yeah, I have it.
Yes, sir.
Maybe later.
Did it sign
I
that?
don't think. Do you need it or for me?
for you.
Okay, no one said anything.
Okay, that's fine. Okay.
I'm
Sorry, yeah.
No problem.
Okay.
Thank you.
Thank you.
Okay, so we have finally obtained this result. Let's examine that closely. If our dt is very small, this whole thing is almost identity, right? So our next state will be nearly the previous state.
Yeah.
And also, we have this delta t linearly in the second term. So if delta t is very small, each and every control is contributing very small to the evolution of the system. And otherwise, if dt is very big, first of all, we'll move a lot from the initial state, and the control will impact the behavior of the system significantly.
Okay.
So, is it clear conceptually, technically? Will you be able to reproduce all of this by yourself?
No.
It needs to test.
Okay, sure. So,
I get the math. I get the math.
uh-huh.
Something with the equilibrium point doesn't sit right in my brain yet.
Ah.
But I get it.
Okay, so you can consider this to be just a formal expression. We are in a search of a point that has this property,
Okay.
and this is mathematically correct.
Yeah,
So,
when I do that, it makes sense. Like the math makes sense.
so it's just for the, we have to find the substitution for this to be of a very specific, easy to analyze way.
Right. And we showed this. Okay, so now we got to this conclusion. We got a hat and b hat.
Yes.
How is this going to help us? Like,
Ah.
in a sense.
That's a good question. So we can do another proof, or we can leave it for tomorrow. So it's not that long, but it's kind of conceptually demanding. It will help us. The short answer is that we'll be able to derive certain controllers from that, optimal controllers. But with the details, my plan was to first derive the continuous LQR and then derive the discrete finite horizon MPC. So we'll need this for two purposes. The first is to derive this predictive controller, and the second is to simulate the system. Because can I erase this? This is the Taylor expansion. The matrix power is set by this series. And here we're taking the approximation of just two first terms. So m to the power of 0, this is the identity, over 0 factorial, which is 1. And the first term is at, because it's m to the power of 1 over 1 factorial. And we disregard the rest of the terms, second, third, and so on. It's an approximation. It is valid only, well, it's valid if dt is small.
Coming back to what I mentioned earlier, like when I saw the code, the xk plus 1 is equal to x dot delta t plus xk, how?
We'll take a look at it now.
Okay.
When I will erase it, we'll move towards the coding part. So how exactly can we reformulate this in the form of the system evolution?
I had a question. So about this part. Here, here instead of A equals C, it was y0, right? Somewhere here, somewhere here.
Here it was
from this, there was a y times zero.
Y times 0. Yes, it was here. I just rewrote it more precisely. So if we move the 0 point to k delta t, it will be exactly that.
But then wouldn't delta t also be zero?
H will be
I thought it was
Here. So we are considering the evolution of the system from this point up to this point in the interval. The only variable here is t. And actually, on the conceptual level, 0 for us is exactly this thing, the beginning of the interval. And delta t is not 0, it's a constant time that is between the frames. Like if we're sampling 100 times per second. Exactly. So we start from this interval and starting from that interval at the moment the beginning plus the evolution is like this. Yeah.
Just substitute B, C will be.
There is a difference. There is a difference. X is the current state, X star is equilibrium, which satisfies the property that X star dot is equal to 0. At equilibrium of X dot is equal to 0. It satisfies that property. So intuitively, I have processed what that means here. This is how we move it somewhere. It makes sense mathematically. Yeah.
Now, like when programming, do we need to know each step in the mathematical
no,
procedure?
not necessarily.
Or only the
We
final?
we don't really need the math to program the robot or to participate in the competition. But I'm trying to build the foundation for the team. Yes. So it's better to be expert in the control systems. That's why we're doing all of this.
But I don't think it's too much math for me. I do understand that, but
Yeah, it will not really be significantly more complicated than this. It's just the linear algebra differential
it's basic
equation.
stuff, yeah.
It's fine.
But this the final equation is the one we need, right? The final equation.
Yes, we're going to use this all the time to integrate the systems.
And
It's very foundational.
A hat and A hat. They are constants?
Yes.
Or-
Because the sampling rate is constant. It's usually constant.
ln of y is equal to 18. So this is plus. You can make x star. Yeah, let's put the plus in. Yeah, you can put the plus in. No, e raised to
This system is new for each timestamp because UK is different for each timestamp. And this system is actually set by a certain vector field.
e raised to c is just another constant. Yeah.
So there's a
E raised to c,
field
you can just
here.
write this as another constant entirely. Like instead of writing e raised to c, you can just write c.
Somewhere in this vector field,
E raised to 18.
there is a
Now,
point
at y is equal
where
to 0.
the derivative is 0.
Sorry, at t is equal
And
to 0.
here we are finding the exact expression for that
z.
point.
That's why you put y of 0. Where is that? But yeah, you get the point. So like that's how so instead of like regular variables,
A hat and B hat are the matrices that say that set the behavior of the discretized version of the system. Other
y is equal to x plus x star. Like mathematics, x star is
That's the mathematical.
Yeah, I think x star is equal to 8 minus 8 because you know.
x star is the thing that.
You know how it like we do like we do minus x is equal to plus x, right? This is like mathematics. So there's no point to do this.
Yeah.
And yet it makes sense because you're counting out.
Yeah.
You're not changing it. It's a trick.
This is different. This x star satisfies the property that x dot at that point is equal to 0. That is, it satisfies that property. That's the check. Why is, if that makes sense, everything else makes sense.
Can you just explain what X star is?
Star is the equilibrium point where x dot is equal to 0.
Yeah.
So it's just
The
some.
position at which your velocity is 0?
No, not really. X is a vector.
Oh no, I forgot.
The-
State function.
Yes, 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 yes. So the tangent of the state vector is 0, which means that the actually this operator A, or this operator, this linear operator, sets a vector field over the state space, and in that vector field, in that point, the vector field is the derivative is 0. So remember we were drawing the evolution of the system, some spirals and stuff, and if we are at any certain point, at the next instant in time we'll be at a different point. At the equilibrium point, we can stay infinitely long. Just the equilibrium point, nothing special, like with the pendulum, upwards, downwards, excuse me. And here it's just for convenience, so it doesn't have any inherent meaning or something.
So at the equilibrium point, regardless of the control we are inputting. So
No. Here the control is already fixed. We are inside this tiny box where we do not change the control. And we are now considering this system. So
okay, so for that specific control that we are applying,
yes.
The
And this equilibrium point could be unattainable. Unattainable, yes.
Okay.
But there's no problem. It's just a formal trick, really. Nothing special.
Okay.
Just a formal trick to bring this form to this form.
Okay, so it doesn't have. Okay, so
Yeah, we don't have to go there.
assume the force is constant. Okay. Assume the control force is constant.
Oh, okay.
Okay. So at what point, given that the control force is constant, would the x dot be 0?
Okay, got it.
It doesn't have to actually be the case. Like that doesn't need to be.
Makes sense.
Okay.
Makes sense. Okay.
Awesome. So now let us talk just a bit about how do we program stuff, given the information we have got here. Let us consider the same example we have considered previously. E dot, the same. So B dot, B double dot, this is the A matrix, this is the B matrix. dt is some value that we will fix, like 100th of a second, for example. And all of these things, they could be considered to be NumPy arrays, so they are programmable in a sense. Let's take a look. So in such a case, A matrix dt, A hat will be equal to 1 on the main diagonal and delta t times this thing over here. So it will be just delta t here and 0 here. And b hat will be equal to delta t times b, times the original matrix. So it's 0 here and delta t 1 over m here. What does this give us? This gives us the awesome opportunity to propagate the system through time. So let's imagine that we have a certain state x naught, and we have generated the control u naught. So it turns out that x1 will be equal to a hat x naught plus b hat u naught, but if we expand it, it will take the following form. So b1 b1 dot is all equal to, I'll just multiply it here directly, delta t 1 0 b naught dot 0 delta t over m f, and what we get is b naught plus delta t b naught dot, and here we are going to get b naught dot plus delta t f over m, which is exactly the Euler integration scheme.
What is that?
The numerical integration. You know that? So it's like multiplying the current velocity by a small time interval and adding
Yeah.
that.
It makes sense intuitively, yeah.
Yes. So we have derived that
Okay.
formula. This is how we are going to get our next state. So we can apply the same once again and get x2. We can program that. We create literally x like a NumPy array. Zero b dot 0, and in order to get the next x, we have to do precisely this: 2 matrix multiplications and 1 vector addition. So this is the way we can program it. And the thing is that it could be applied to any system, not only to this system. This is the special case for this system. But if we are able to write down something in the form of a linear system, we can integrate it like this, and it will it will be proper, so to say. It really is based on the way in which the differential, the dynamical systems evolve in time. So it could be applied to the same chair, but with higher number of dimensions, so that we can consider this to be a system with 2 linear and 1 rotary degree of freedom, and its behavior will be indeed guided by the same system, but with higher dimensions. So we can integrate all of this. I'm applying some force, and the entirety of the system is evolving, and we can approximate that with numerical integration. The smaller the step, the longer it takes to simulate, but the more precise the results are.
We ignored the higher order terms when you were deriving it, right? Does that make a difference? I mean, this is a linear equation, sure.
Yes.
Suppose we didn't, like, I mean, how much of a difference does that make? If that is a good question to ask.
It's a fine question, yes.
This is one.
So, if we did not disregard those terms, we will get a quadratic expression in terms of the, let's write it down. Let's take the next approximation. Okay, so e to the power of t is equal to, or is approximately an identity matrix plus a t plus a square t squared over 2. So if we do that, we will get the more precise version of the evolution of the system. Can you remove the left part?
Oh, that's not.
So could you remind me x of k delta t plus t was equal to I plus at plus a square t over 2? I'm taking this more precise approximation, and it was multiplied by x of k delta t minus or plus. What was it?
Wasn't it minus a inverse c?
Minus a inverse c, right? Can you check the notes?
I was not taking notes. I was trying to understand it. So I realized I'm dividing by that.
No,
It's plus a inverse c and then minus outside.
Plus a inverse c and then minus a inverse c over here. Okay, so we took the next approximation. More precise. Let's take a look. I'll just expand everything. Let's see what sticks. Okay. So what do we see here? These guys cancel out. This inverse is cancelled with the one of the powers of a. These are cancelled, and we get k delta t. So it's basically the same approximation times xk over here. Yeah, yes. Plus t c over 2. Wait, excuse me, a t Okay, so we have got this better approximation, but so okay, let's reorder stuff once again. See what will happen, and also we can plug a C over here. C was equal to what exactly? B UK, right? Okay, so it's identity plus C plus square over 2 x k plus k delta z, and here is the last part, which is A, C, B, U, K over 2. You keep the track of what's going on, right?
Yeah.
Okay. So we can propagate the system like this. Indeed. It's not inherently bad or anything like this. So this will be our matrix A, big head or something, head two heads. And this will be the matrix of B to head. We indeed can use these approximations. It is
At that
possible.
point, would it be different from, like, we came to the conclusion that's the same as like numerical integration, right? How would it, I mean,
How would it affect?
like numerical integration makes sense intuitively. Now,
Mhm.
if we had, like, if you play it out, would it look similar? Like, I mean, not that we should play it out. but
Okay, yes. Let's take a look at B at A down at this one. For our special case, so it will be 1 delta t 0. It's the same. And now let us add the last term, which is t square and a squared. So we have to square this. Seems like it's just 0, right? This problem.
Yeah.
So surprisingly, for this exact case, for this specific system, this matrix is the same, so it will not make any difference. But that's
good.
that could not be generalized to other systems. The system is very simple because it's a block and it's accelerating with the it's accelerating being driven by a single force. So if it would be a block on a spring, it will be completely different. The matrix of evolution will be different. And in more complicated cases, these matrices with higher order terms indeed could be different. So the integration will be slightly different. But the general framework will be the same. We'll just have some higher order terms like delta t squared times something. That's what we'll have. That was a good question. And yeah, so there are other integration schemes. This integration scheme actually does not conserve the energy, and we get a numerical error increasing. We can try to mitigate that.
When you say integration scheme, what do you mean? Like a way to
How do we propagate the system from x0 to x1?
Okay,
This is the
okay.
numerical integration. We're doing literally that. So there is lot of velocity by time, and there is something going on, and we are trying to numerically approximate the path. And we are taking a very, very simple approach, something like this. So the smaller the dt is, the better it works. There are other integration schemes like symplectic Euler. It's slightly better. We can derive that tomorrow if you would like to. Just there the error is smaller.
Okay.
But I think for today we are done.
Yeah.
We have laid the groundwork for the derivation of LQR that is going to take a big part of tomorrow. That will be fun. Thank you for coming.
Do we need to learn anything about ARE or any of those things? What do we need to? What are some of the prerequisites we would need to know to learn LQR?
No real prerequisites like linear algebra, differential equations.
So
You
I
already
do not
know
need
it.
to know that ARE algebraic Riccati equation.
No, we'll talk about that. That's fine.